I consider myself a simple man. I like things that go real fast, like cars, motorcycles, and Husker football. One night, while walking my dog, I saw a light race across the sky, and I said, "Whoa, what's that? That looks fast." My neighbor said, that's the International Space Station. The International what? So I raced home and jumped on the internet to ask that Jeeves fella about it, and he said there's a spaceship racing around the world at 17,500 miles per hour, circling the entire planet in 90 minutes. I said, wow, that's fast. So I decided to quit my job and go be a rocket scientist. A few years book learning later, I find myself in a schoolroom with a teaching lady, who everyone calls a doctor for some reason, and she's telling me to do a presentation on some topic we covered that I'm, quote, unfamiliar with. I said, teaching lady? That don't narrow it down much. However, I found myself feeling partial towards some stuff she told us about Halley's Comet, and I think you will too, but we got to cover some basics if anyone wants to truly understand how cool and how fast it is. So here goes. Some nerd named Isaac Newton thought up with some rules a long time ago that he noticed all things follow when they're moving. To demonstrate, let's put our friend Hank here in the vacuum of intergalactic space. Hank floats at this point in space, and nothing he does can move him from that point. He can flail around all he wants, but there's nothing for him to push off of or swim through, so he's stuck at that spot until some kind of force acts on him. So you round up your boys, you grab that tater can that took out Miss Bell's window back in 8th grade, and place yourselves 200 feet away from Hank. When you fire that 5-ounce tater at Hank at about 125 feet per second, you notice two things. Number one, the tater flies in a straight line towards Hank, and number two, you find yourself moving away from your friends in an opposite direction to that tater. When that tater hits Hank, him and that tater move away from his spot in space at a speed pretty close to the one you're moving away from yours. And now you're both moving away forever until you hit something, or if you can turn around and fire that tater cannon in the direction that you're moving. Now, when you all had that tater cannon back in 8th grade, you aimed it directly at Hank, and that tater hit the ground about halfway between you. You put in another load, aimed it at about a 45-degree angle above Hank, and that puppy flew 300 feet past him right into that window. Why did the potato fly in a straight line in space but not in Penfield, Ohio? Was that Newton guy wrong? Well, no. You see, in space, that tater had one force acting on it in one direction, so it went in that direction. On Earth, a force called gravity is constantly pulling down on everything. And the air the potato is flying through acts like a billion tiny Hanks that it runs into, slowing it down in the direction that it's going. These two forces change the direction of the potato that you fired with the force of the cannon, making it follow a curved line with a $2 name, a parabola. Now, let's take away the air and put us on the moon. If you fire that same tater at the same angle, the lack of tiny Hank slowing it down and the weaker gravity means it flies about 3,000 feet away instead of 500. Now let's put Hank down on his mark. You load up enough gas in that can to send that tater directly at Hank at 5,500 feet per second. However, that jerk flinches right as you pull the trigger and that tater flies right past him. You expect it to hit the ground, but the tater is moving so fast that the force of gravity pulling it down towards the moon makes the parabola the same shape as the curvature of the moon itself. After about 108 minutes of shooting taters at Hank, that second tater comes around and hits you in the back of the head at 5,500 feet per second. Ain't fun now, is it? Congratulations, you just discovered orbit. A bunch of Soviet nerds were the first to make this happen around the Earth back in 1957, and the world got to liking it so much we've been doing it ever since. In 1998, America and the Russians built the International Space Station by launching a rocket above the atmosphere and then launching another rocket to make it go 17,500 miles per hour, reaching a circular orbit. Since there's nothing for the ISS to run into, it keeps circling the Earth nonstop. Now that you know what orbit is, we can look at our own solar system and see how things are orbiting the sun. Since there's no real up or down dictating the motion of things in space, we use the main body of the solar system as a reference frame so we can actually talk about the motion. In this case, we use the sun. You'll notice that everything seems to be moving the same direction around the sun that happens to be the same direction the sun rotates. The Latin term for walking in the forward direction is progradus, the walk in the opposite direction is called retrogradus, so we'll call this direction prograde and the motion in this direction retrograde. Alright, so you might be wondering, why the heck does the stuff closer to the sun go zip around faster than the stuff that's further out? Well, imagine you're spinning a ball on a string around your head. If you spin it real fast on a short string, that ball stays close to your head, but as you let the string out, the ball starts to swing around a little bit slower as you go further out. That's kind of like how things work with the sun. Gravity acts like that string, and all the stuff in the sky is constantly stuck in a circle until something can hit it hard enough to change its path. If the Earth was on a string that has the length of a yardstick, Mercury would be on a string that's 16 inches long, going around your head almost 5 times for every one loop the Earth makes. However, Neptune, on its 30-yard string, takes about 165 Earth circles to go around once. Another small detail to note is that although the Sun contains 99.9% of the mass of our solar system, the planets don't orbit the Sun itself. Rather, everything, including the Sun, orbits a point just outside the surface of the Sun called a barycenter. The same way a grown-up has to lean back to swing a kid around the point where they're both spinning, the sun is just as much a victim of physics as the rest of us. Looking at what the stuff in space is made of, you'll notice a pattern in our solar system that's worth analyzing. So you've got Mercury, Venus, Earth, Mars, a big old field of rocky debris, all tucked within a radius of about 3 Earth-Sun distances, with another $2 name of astronomical units, or AU for short. All these are made of mostly rock and metal, and some gas is held on their surface by gravity. Following this, there's a whole lot of nothing until we reach Jupiter at 5 AU, which is a big old ball of gas with no solid core, yet it's still over 300 times as massive as the Earth. The gravity here is so strong that stuff flying through space that might hit the Earth gets sucked into Jupiter. Traversing through a whole lot more nothing for 5 more AU, we come across Saturn, another big ball of gas with almost 100 times the mass of the Earth. Real quick, you see them rings? They're made up of really small rocks, and the width of the rings is about 4.5 times the diameter of the Earth, but the height doesn't get much bigger than an American football field. After going through almost twice the distance of Saturn, through nothing, we find another giant planet, Uranus, with about 14 times the mass of the Earth. Then another 10 AU later, we have Neptune with 17 times the mass of the Earth. After this, there's a whole heap of rocky bodies floating in what's called the Kuiper Belt between 30 and 50 AU. Included in the Kuiper Belt are 5 dwarf planets, Orcus, Pluto, Haumea, Quaoar, Makemake, which all pale in comparison to most of the moons in our solar system. We acknowledge these bodies in the Kuiper Belt, as well as Ceres in the asteroid belt, by calling them dwarf planets. But since they haven't cleared their orbits of other debris that can change their motion, we can't call them planets. So we've got 5 terrestrial planets and some debris within 3 AU, all of which have a combined mass of less than 1/5 of Saturn, followed by 37 AU of nothing but gas giants and ice planets, and then a belt of rocky debris totaling about 1/20th mass of the Earth. Now, although the rocky bodies in our solar system are a fraction of the total mass, they play a crucial role in understanding the formation of our solar system. So how did all this come to be? Well, since we have so many heavy atoms in these rocky bodies, a bunch of people way smarter than me have concluded that our solar system had to have formed when 2 super dense neutron stars decided to have a little dance. When these 2 stars collided, they created a massive explosion, spewing out a ton of gas and dust into space, which we can look up in the night sky now and see this process happening all over the place. These giant gas clouds reach a critical point where it collapses in on itself to form a star. All the debris from this collapse starts swirling around the star, running into each other from every which way. Some collisions make the stuff fall into the star, and eventually the stuff that's left over is all going in the same direction, relatively along the same plane, forming what is called a protoplanetary disk. Now, closer to the center, where it's hotter, these gas and dust particles start sticking together, forming solid clumps, and over time, these clumps get bigger and bigger, forming what we call rocky planets. But as you move further out, where it's colder, the gas doesn't solidify as easily. Instead, it just sort of accumulates, forming a thick, dense collection of gas, which results in a larger gravitational field, which more stuff gets pulled into. This is how the gaseous giants like Jupiter and Saturn came to be. Beyond them, in the even colder regions, you get a mix of gas and ice, leading to the formation of ice giants like Uranus and Neptune. So in a nutshell, where you are in the protoplanetary disk determines what you're made of. Rock and metal closer in, gas and ice further out. Now, what I've described to you about the solar system is incomplete, with values rounded recklessly and some details left out for the sake of brevity. I can already hear them astronomy nerds clacking on their keyboards maliciously, wishing me and my family harm because I didn't mention Jupiter's Greek Trojan asteroids, or the details of gravitational lensing to form planets from planetesimals. But this basic foundation is needed to truly appreciate Halley's Comet. We're getting there. That explosion from the neutron star collision made a lot of stuff, and then the physics of the protoplanetary disk formation organized most of that stuff into categories based on how far the stuff was from the star, being our sun. However, there's a lot of smaller stuff in between that gets their own category based on what they're made of or their orbit compared to other planets. When you think of an asteroid, pop culture has in your head that these are big solid rocks floating around in space. Although about 3/4 of the smaller debris in our solar system is classified as rocky, made up of clay and silicate, the larger these asteroids have enough gravity to act like a space Roomba, sucking up every speck of dust in their path. A recent mission to the near-Earth asteroid, Bennu, intended for the probe to touch the surface and blast some nitrogen gas to stir up this dust so we could bring it back to Earth and poke at it with sticks and stuff. What happened instead was a probe arm plunged almost 2 feet deep into the dust-coated surface of the asteroid. So they blasted the thrusters and pulled out before the probe completely sank in. Since Bennu is a rocky asteroid that orbits the sun real close to the Earth, we can assume it originated here, and we can expect to find stuff on it that formed in a similar part of the protoplanetary disk. Halley's Comet itself is a 242 billion ton chunk of ice composed of 80% water, 3% carbon dioxide, 17% carbon monoxide, and minor traces of other particulates it picks up along the way, all from the Kuiper Belt region where we think it formed in the protoplanetary disk. What makes it so wild is it has what we call an eccentric orbit, which reaches out 5 AU beyond Neptune into the Kuiper Belt and rips right back in around the Sun just outside the orbit of Mercury. And it's doing all of that going the wrong way around the Sun. Retrograde. Discovering this gave me flashbacks when Gam Gam had her episode and took us the wrong way in I-20 so she could get that airplane off the porch before the price of eggs got too high. And I mean, I like going fast, but I just hope Halley's Comet is right with Jesus. As closest point to the Sun, that 200 billion ton ice ball is moving about 123,000 miles per hour, whipping back out into space and reaching its furthest point about 38 years later, where it's moving about 2,200 miles per hour. This means Halley's Comet completes an orbit out past Neptune and around the Sun every 76 years. The last time we saw it was in February 1986, which is about 38 years ago at the time of this video. After noticing the aphelion date was close approaching for December 2023, I asked that teaching lady if she could help me with the math to calculate exactly when Halley's reaches its furthest point, and she said, well, we can't calculate its orbit that exactly. This ripped the rug of orbital mechanics out from under me. Did those nerds Newton and Kepler not know what they were talking about? Well, no. When you ask that G's feller to show you pictures of Halley's Comet, you're going to see something like this. This is what public school has us thinking comets look like, flying through the darkness of space with the tail behind it, like a smoke trail behind a little man with a big ego, rolling coal in the interstate. However, like with our friend Hank earlier, there's nothing in the vacuum of space to act on the comet to cause this tail, until it gets close to the Sun. What we see from Earth is not the tail of the comet following its path. Instead, the Sun is blasting out a constant stream of charged particles called solar wind. When Halley's Comet gets close to the Sun, the heat from the solar wind causes the ice in the comet to vaporize, releasing gas and dust. This material then gets pushed by the solar wind, creating that glowing tail we associate with comets. But here's the kicker. The tail always points away from the Sun, regardless of the direction the comet is moving. So when the comet is racing towards the Sun, its tail is trailing behind it, but as it rounds the Sun and starts heading back out of the solar system, that tail is actually leading the way, still pointing away from the Sun. It's like if you're running through a big windstorm with a flag, the flag would always blow away from the direction of the wind no matter which way you're running. So, when we see Halley's Comet with that brilliant tail, it's not leaving a trail like a car leaves dust on a dirt road. Instead, it's getting blasted by the Sun's solar wind, shooting out a tail debris radially from the point in the comet's orbit. This interaction with the Sun not only gives us the spectacular visual display, but since it's losing that mass, the opposite of the potato hitting Hank is happening, which slightly changes the comet's path each time, making its exact return date a bit unpredictable. However, NASA's Jet Propulsion Laboratory calculated the trajectory of Halley's Comet after it stopped losing mass, and they predicted its aphelion date and time to be just after 1 a.m. Universal Coordinated Time, which will be December 7th, 2023 at 8 p.m. Eastern Standard Time, 6 p.m. Mountain Time. So, if you're looking for something to celebrate between Thanksgiving and Christmas, gather your friends around and count down the moment to where this chunk of ice, which formed from the same ice that makes Uranus and Neptune, is turning around and making its way back to us. Then, in 38 years, you and the grandchildren of those people can marvel at the beauty of this spectacle, and you'll be able to talk about it like a book-smart nerd that understands the cosmos. So, the next time you're looking up in the night sky, think about all them planets and comets zipping around out there, each with their own speed and path. All thanks to that big old ball of gas we call the Sun tugging on them strings. And remember, even a simple man can understand the wonders of the universe if he's got a curious mind and tater cannon.